So this is lesson 6.5. A is an alpha, rational functions and rational equations. Not sure how many videos this will take, probably 3-ish. But what we're going to do here is look at rational functions first of all. And basically what we're talking about when we're talking about a rational function is something that looks like this. Has variables in it and is in the form of a fraction. Which means that we have a function on top and a function on bottom, and the top and bottom are both polynomials where the bottom number cannot be equal to 0, because if this number here was 0, so if x were -2, that'd be 0 squared. That would make that a 0, which would make it undefined. So therefore, the bottom number cannot be 0 because we don't want it undefined, yet we're going to use the bottom number as a 0 in order to find some things out. And you will find that out in calculus as well, that you're going to try to make the denominator 0 because there's, 0, so it's undefined, so you can find some stuff out. Okay, so anyway, we're going to look at what is called a vertical asymptote, which you should have some experience in, a horizontal asymptote, and finally what is called a slant asymptote. So we're going to kind of look at each one of those. So we're going to start with the vertical asymptote, which you've already looked at. And let me just throw a picture of one out here, especially for this equation that I have right here. Okay, so here is a picture. It's figure 6.39 in your book. For example 1, here is our rational function, and here is our vertical asymptote. Now the way you find this vertical asymptote is you set the denominator to 0, and whatever number makes this 0, then that is our vertical asymptote. So if we were to do that, take the square root of both sides, we get x plus 2 equals 0, so x equals -2. So that makes this undefined. What undefined means here is that our graph cannot touch this answer, -2. So we go over x is -2, and we draw a vertical line. And that means that the graph is going to go into infinity, and it's going to come this way into infinity, and it's going to get closer and closer and closer to this -2. But no matter how close it gets down here into negative infinity, it will never touch it. So that is one of the weird things about math, is it gets closer and closer and closer, yet it never ever gets there. It doesn't matter how far into infinity you go, which always seemed weird to me. Because as you get closer and closer and closer, someday you'd think you're going to get there. But you can take the distance from here to here. Doesn't matter how close this is, but you can always take half of it. And then this distance from here to here, you can take half of it. So you can always take half of it, which means you never quite get there. So if that helps you understand what's going on. Anyway, that's example 1. Let's jump to example 2. Not getting into anything scary yet. Cost benefit. Suppose that for specified values of p, the function c of p equals 800 p over 100 minus p. Okay, so can be used to model the cost of removing p% of a particular pollution from the exhaust gases at an industrial site. Okay, so what this says is, this is how much it's going to cost us to take the pollution out of, well, I guess at the chimney of the factory. That's the cost. So I would imagine that as we take more and more of the pollution out of the industrial site, it's going to cost us more money. So what they're asking you to do, first of all, is graph the function, and it gives you the windows. All right, so then it says, does this graph of the function have a vertical asymptote? And the answer will be yes. If you look at page 480, it will give you the graph. And the graph looks something like this. And we have a vertical asymptote. Now, you can just look at this and say, okay, what's going to make that 0? Well, if p is 100, that will make it 0. So my vertical asymptote is 100. Okay, so C says, for what values of p does this function serve as a model for the cost of removing a particulate pollution? Okay, well, we know this part of the graph right here is the one that we want to look at, because it continues costing more as our percent gets higher and higher and higher, so that's what we want. But we don't want this here because we're not going to go into negatives. It can't cost us negative. So actually, what we want here is only this part of this graph. Okay, this part down here, we're still in negative territory. This part here, we're in negative territory. So this is going to be positive. This number here is the cost as we approach 100%, but we never reach 100%. How do we know that? Well, because you can never take 100% of the pollution out of the air. There will always be something left. Okay, so that's why it's the asymptote. So there's our information that we're interested in. So at 50%, it will cost this much. At 99%, it's going to cost a lot. Okay, so the less we take out, the less it's going to cost. So E kind of answered that, and let's just keep going on here. That's vertical. Vertical asymptotes, pretty easy to do, and not going to give you much trouble. So what we're going to do now is look at horizontal asymptotes. Okay, so horizontal are the ones that go from left to right. So let's get us a graph here, and let's draw the asymptote for 3 over x plus 1. Okay, so I'm going to have a graph that goes like that, and then the other part of the graph is going to go like that. Now notice I also have my vertical asymptote at x equals -1, because that makes our denominator 0. So we do have a vertical asymptote, but we're going to focus on the horizontal asymptote in this particular problem. Okay. There are some rules to determine the horizontal asymptotes of a rational function. The rules are, if the degree of the numerator, so if the degree of numerator is less than the degree of denominator. Okay, so for example, if we had x squared plus 3 over x cubed minus 4. Okay, let's make that an x to the 5th. So my numerator is less than my denominator. Okay, the exponent is. If that's the case, then y equals 0, meaning the asymptote is on the x-axis, which is the case that we have in this one. See, notice, we don't have an exponent on the 3. We don't have a variable. Okay, so it automatically is nothing. Okay, this x here, we have a 1. So the numerator is less than the denominator, so therefore our asymptote is on the x-axis. It does not cross the x-axis. Okay, now sometimes your graph will cross the x-axis, even though the x-axis may be an asymptote, meaning it might look like this, and then never touch it. So it may go across it, but then it'll go and never touch it again. So horizontal asymptote can cross it, okay? But the end behavior, which is over here, will never cross it again, okay? And that's what we're looking at here, is we're looking at the end behavior, what happens at the end of the graph. Okay, so this is one situation that can happen. The degree of the numerator is less than the degree of the denominator. Let's say that the numerator equals the denominator. The degrees are equal, okay? If that's the case, we have a horizontal asymptote, and this is kind of odd, but we have a horizontal asymptote at the ratio of the leading coefficients. So let me just kind of make one up to show you an example. 2x squared plus 3 over 5x squared minus 6. All right, so my degree of the numerator is 2, the degree of the denominator is 2, so they're the same. So therefore, we take the ratio of the lead coefficients. So my horizontal asymptote is at 2/5, meaning my horizontal asymptote, well, let's say that that's 1. 2/5 is a little less than half. So my horizontal asymptote would be at y equals 2/5. Okay, and that's when the leading coefficient is the same. Okay, we said the numerator is less than, equal to. Now let's say the numerator is greater than the denominator. So it'd be like x cubed plus 6 over x minus 6. My numerator is higher. Whenever the numerator is bigger than the denominator in their degree, there is no asymptote. Okay? Doesn't exist. All right, so those are your three options that I would write down, top of page 481, of your horizontal asymptote, how to determine where it is. So it's pretty easy to do that. Okay, so let's look at example number 6. Okay, some reason my brain is really working slow today, so if I'm kind of stopping and you're wondering what the heck am I doing, it's because my brain fell asleep. All right, so this is example 3. Okay, first of all, I like to write this in the right order, in decreasing order. See, my brain just isn't working. So 2, 1, 0. So I've got it like that. All right, so I graph this. It's asking me to graph it. And when I graph it, I get, well, let me just give you the picture from the book. So the first question is, does this graph have a horizontal asymptote? Well, one of the things that you'll notice here is that our numerator coefficient, or not coefficient, our degree of our numerator is greater than the degree of the denominator, which is step 3. So therefore, it has no horizontal asymptote. Okay, so B says, does the graph, that is B. C. Graph the function on the window, 0, 20, and 0, 50. So you do that, and when you do that, you get this graph here, because 0 to 50 instead of, from like the first one said, negative 20 to 20 and negative 30 to 50. So this shows both. This shows the graph of the whole equation. This just shows this part of it. Okay, so why do they care about that? Well, because does the graph of the function using the window in part A or B better model the average cost function? Well, this is a better representation of the cost function because our numbers are positive. We cannot have negative dollars, okay, because this has to do with C of X is the daily average cost for the production of Stanley golf carts. It can't cost a negative dollar, so we can't use these, and we can't sell a negative number of golf carts, so that we're only going to use this one here, although the actual graph includes both of those. All right, so E, use technology to find the minimum daily average cost in the number of golf carts that gives the minimum daily average cost. So we're looking at minimum. So we're looking at somewhere down in here. So the minimum would be, it looks like 4, somewhere between 4 and 6 maybe. We could find out exactly what it is using your calculator, and it ends up being y is 23 and x is 5, which means that the average cost is $2,300 per golf cart if we produce 5. Okay, so that's why these graphs are nice, is you can look at the minimums or the maximums, which in this case there isn't, and be able to get some information there that we can actually use rather than just a bunch of numbers and things that you really can't use. Okay, so I'm going to stop this here before we go into slant asymptotes and missing points, because that's kind of tricky but not too bad, but I think we might be able to do it in 2 videos.